In the past few years, we've seen artificial intelligence evolve from a niche research field into a transformative force reshaping how we work, create, and interact with technology. At the heart of this revolution are large language models, systems trained on vast amounts of text that can generate human-like language, reason through complex problems, and even write code. But how do these models actually work? What's really going on inside the black box? Today, we're diving deep into the inner workings of modern AI, specifically the architecture, training process, and mechanisms behind large language models like GPT, Llama, and Claude. Let's start with the foundation, the transformer architecture. Introduced in 2017 by Vaswani et al. In the paper Attention is All You Need, this model design fundamentally changed how we build language models. Unlike earlier models that process text sequentially, like reading a book from left to right, the transformer uses a mechanism called self-attention. This allows every word in a sentence to dynamically interact with every other word, regardless of distance. For example, in the sentence, "The cat sat on the mat," the word cat can instantly attend to mat even though they're not adjacent. This parallel processing capability is what makes transformers so powerful and efficient at capturing long-range dependencies. Each transformer layer consists of two key components, the multi-head self-attention mechanism and the feed-forward neural network. In self-attention, the model computes three vectors for each word: a query, a key, and a value. The query from one word is compared to the keys of all other words to determine relevance. This produces a set of attention weights, essentially a score indicating how much focus each word should receive. These weights are then used to weight the values, producing a contextually enriched representation of the input. The multi-head part means this process happens in parallel across multiple attention heads, each capturing different types of relationships, syntactic, semantic, even discourse-level patterns. This allows the model to understand meaning at multiple levels simultaneously. After self-attention, the output passes through a feed-forward network, a simple but effective stack of linear transformations with nonlinear activation functions like GLU. This layer processes each position independently, adding nonlinearity and increasing representational capacity. These two components are repeated across multiple layers, typically 24 to 100 in modern models, allowing the model to build increasingly abstract representations of language as information flows deeper. Now let's talk about how these models are trained. The process begins with massive datasets, often hundreds of billions of tokens drawn from books, websites, code repositories, and more. The training objective is next token prediction. Given a sequence of words, the model learns to predict the most likely next word. This seems simple, but it's incredibly powerful. Over time, the model learns statistical patterns in language, grammar, syntax, factual knowledge, even reasoning chains. It's not memorizing the data. It's learning a compressed, probabilistic representation of language itself. Training happens in two phases, pre-training and fine-tuning. During pre-training, the model is exposed to raw, unstructured text across diverse domains. This phase can take weeks or months on thousands of GPUs or TPUs. The model learns general language understanding, how to describe the world, explain concepts, or generate coherent text. But it's not yet aligned with human intent. It can be verbose, inaccurate, or even harmful. That's where fine-tuning comes in. After pre-training, the model undergoes supervised fine-tuning, SFT, where it's trained on a smaller dataset of human-generated prompts and desired responses. This helps align the model's behavior with human expectations, making it more helpful, truthful, and safe. But even after SFT, the model can still be inconsistent or prone to hallucinations. So the next step is reinforcement learning from human feedback, RLHF. Here, human raters evaluate multiple model responses to the same prompt and rank them. These rankings are used to train a reward model that learns to predict what humans prefer. Then, using algorithms like proximal policy optimization, PPO, the language model is further fine-tuned to maximize the reward signal, effectively learning to produce outputs that humans find more useful and trustworthy. This training pipeline is not just about performance, it's about alignment. The goal is to build models that don't just generate fluent text, but do so in a way that's useful, ethical, and safe. And as models grow larger, the complexity of this alignment task increases exponentially. Now let's zoom in on inference, the moment the model actually answers your question. When you type a prompt into ChatGPT, the model doesn't retrieve a stored answer. Instead, it generates the response token by token, using the context of your input and its internal parameters. This process is called autoregressive generation. At each step, the model predicts the next word based on all previous words, then appends it to the sequence and repeats. The result is a fluent, coherent response that feels like a conversation. But there's a trade-off: speed. The longer the output, the more computational cost. That's why techniques like speculative decoding and KV caching are used. KV caching stores the key and value vectors from earlier attention computations, so the model doesn't have to recompute them for each new token. This dramatically speeds up inference, especially for long conversations. And let's not forget the role of context length, the number of tokens the model can process at once. Early models were limited to a few hundred tokens, but today's models like GPT-4 Turbo or Llama 3 can handle tens of thousands. This enables complex tasks, summarizing long documents, analyzing entire code bases, or maintaining coherent multi-turn dialogues over long stretches. But here's a crucial point. The model doesn't know anything in the way humans do. It doesn't store facts in memory. Instead, it predicts the next token based on patterns it's seen during training. If a fact is rare or ambiguous, it might hallucinate, generate something plausible but incorrect. That's why retrieval-augmented generation, RAG, has become increasingly important. In RAG, the model is paired with an external knowledge base, like a database or search engine. Before generating a response, it retrieves relevant information, which is then fed into the model as context. This dramatically improves accuracy and reduces hallucination, making the model more reliable for real-world applications. Finally, let's talk about the future. The field is moving toward multimodal models that understand not just text, but images, audio, and video. Models like GPT-4V and Llama 3 Vision can analyze visual scenes and describe them in detail. This opens up new possibilities in education, healthcare, and accessibility. We're also seeing advances in efficiency, smaller models that perform nearly as well as massive ones through techniques like quantization, distillation, and sparse activation. This makes AI more accessible and deployable on edge devices. And as models grow more capable, so does the need for robust evaluation frameworks, transparency tools, and ethical guardrails. The challenge isn't just building smarter models, it's building trustworthy ones. So what does this mean for you? Whether you're a developer, student, or curious learner, understanding how these models work gives you a powerful edge. You'll be better equipped to use them effectively, critically evaluate their outputs, and contribute to shaping the future of AI. AI isn't magic. It's math, data, and engineering, deeply technical but profoundly transformative. And the more we understand it, the better we can harness it for good.